So we'll start the class. Just give me a minute. Okay. So we are dealing with the general organic chemistry lesson, right? So today we are going to continue this lesson. So in the previous lecture, if you remember, we have been discussing about the reaction intermediates, right? There are three reaction intermediates. One is a free radical, and the second one is carbocation, and the third intermediate is carbanion. Third intermediate is carbanion, right? So in the previous class, we have discussed the informations and the very important points under free radicals. So we have completed the free radicals, and today I am going to get into the carbocation intermediate. All right. So we'll start with it. So let me take a methyl carbocation. The formula for methyl carbocation is CH3 plus. CH3 plus. You all know that cation means it is a positively charged species, right? So a carbon bearing a positive charge is called as carbocation. So carbocations are formed by heterolytic cleavage of bond, right? So we have discussed about two cleavages, right? One is homolytic cleavage and the other one is heterolytic cleavage. So the carbocation is formed by the heterolytic cleavage of the bonds, and it is positively charged species, okay? So which has one MTP orbital. So this is the MTP orbital, which you can see. And this carbocation is an intermediate, right? So it is highly unstable. It is highly unstable, and the hybridization of carbocation is sp2. So this is very important. Hybridization of the carbocation is sp2, and cation means it loses its electron. Okay, the one which is electron deficient is called as carbocation. Okay, and here it acts as a Lewis acid. Lewis acid means electron acceptor. So why it is acting as a Lewis acid? Because it has MTP orbital which can accept the electron pair from the other atom. Okay, so that is how it is acting as a Lewis acid, and also it is acting as an electrophile. You all know what is electrophile, right? So E plus is called as electrophile, and electrophiles are electron deficient species, right? A nucleophile will come and attack the electrophile. So carbocation is also a Lewis acid. It is also an electrophile, which is electron deficient in nature. So the nucleophile can come or the anion can come and attack the carbocation. Okay. So these are the informations you should know about carbocation. It is also trigonal planar in geometry only. So like carbon free radical, which we have discussed, carbocation is also trigonal planar in geometry, because hybridization is same as that of free radical, right? So sp2 hybridization means the geometry will be trigonal planar. Clear? So guys, can you able to understand the carbocation and its related points? Do you have any doubt? General Organic Chemistry chapter, my dear. Some basic concepts of organic chemistry. You have one lesson in your book with that name, right? Some basic concepts of organic chemistry. So we are discussing that. We have already completed 5 lectures on this lesson. And this is the 6th session or the 6th class of this lesson. All right. So students, others, can you able to understand carbocation information? So shall we go for the third intermediate, which is a carbanion? Shall we move for carbanion? Chandu, Devananda, Shimoga students, Siriam, Sriniti. Able to understand? Shall we go for the next? Shall we go for the next? Let me know your answer in the chat box, students. Am I audible to all of you? Hello? Am I audible? Yeah. Okay. Okay. All right. All right. So now let's go ahead with carbanion. Carbanion, for example, I'm going to take CH3 minus as a carbanion for you. Okay. CH3 minus is the methyl carbanion. So as you know, that carbanion is also formed by the heterolytic cleavage of bonds. Both carbocation and carbanions are formed by the heterolytic cleavage of bonds. Okay. So unlike carbocation, carbanion is a negatively charged species. Okay. Anion means it is negative, right? It is a negatively charged species which has one lone pair in its hybridized orbital. Okay. Lone pair of electron is present for carbanion. So it is also highly unstable because it is an intermediate. And the hybridization, if you see, it is sp3. So carbon-free radical and carbocation. So those two have sp2 hybridization and carbanion's hybridization is sp3. Okay. It is sp3. And that's why the structure is looking like a tetrahedral. Okay. sp3 means the geometry will be tetrahedral, right? So it is looking like a tetrahedral. And it is an electron-rich compound. It is an electron-rich compound. It acts as a Lewis base as well as nucleophile. So what are Lewis bases? Lewis bases are the compounds which are electron donors. Okay, electron donors are called as Lewis bases. So since carbanion is having one lone pair of electron, it can donate its electron to the other atom and can form the bond. And so it can act as a Lewis base. Okay, as well as it is a nucleophile. Nucleophiles are electron-rich species, right? Nucleophiles are electron-rich species. Carbanion is electron-rich in nature, so that's why it acts as a nucleophile. Clear? So these are the informations about the carbanion. Okay, hybridization is very important. All right. So now we have completed the informations related to all the three intermediates, which are free radical, carbocation, and carbanion. So now we are going to study or learn the stability of these intermediates. Okay, stability of these intermediates. So first, let me take the free radical. First, let me take the free radical. So the radical that we have discussed is CH3 dot, right? So this radical is called as methyl free radical. This is called as methyl free radical. So if I replace one of these hydrogen by alkyl group, alkyl groups are represented by R. Okay. So if I replace one of this hydrogen by alkyl group, I will get RCH2 dot. So if I have RCH2 dot, it is called as primary free radical, which is denoted by 1 and degree. Okay, 1 degree. But we should not call it as 1 degree, it is primary. And if I replace the second hydrogen also by alkyl group, what I will get? I will have R2CH dot. Okay, dot means electron. So this is called as secondary free radical. If I replace all the three hydrogens by alkyl group, I will have R3C, right? R called as tertiary free radical. Tertiary free radical. So among these four free radical, the tertiary free radical will be more stable. Then your secondary, then primary, then the least stable free radical is methyl. Okay. So I will give you the reason for the stability in the upcoming topics, the electronic displacement effects. We will discuss those things, so don't worry. So for now, you keep in mind that the tertiary free radical is more stable. The methyl free radical is the least stable. Okay. Now let's go for the second intermediate. Second, we have discussed carbocation, right? Second is carbo. So in the same way, we have discussed CH3 plus methyl carbocation. If I replace the hydrogen, I will get RCH2 plus, which is called as primary carbocation. And R2CH plus is called as secondary carbocation. R3C is called as, C plus is called as tertiary carbocation. Okay. Now, which one is more stable? Again, tertiary carbocation is more stable. Okay. Then your secondary, then primary, then methyl. Clear? So, free radical and carbocation follows the same stability order. Now, let's go for carbanion. What is the formula for methyl carbanion? It is CH3 minus. So, this is methyl carbanion. And RCH2 minus is called as primary carbanion, and R2CH is called as secondary carbanion. R3C is called as tertiary carbanion. Now, if you look into the stability order, the methyl carbanion will be more stable. Then primary, then secondary, and then tertiary. Clear? So the free radical and the carbocation follows one order, and the carbanion order is the opposite of the other two. So the stability of these intermediates are very, very, very important. So you should know the correct order of these three. So is it fine for all of you? Do you have any doubts in the stability part? Do you have any doubts in the stability part, students? Okay, all right. Okay, students. So with this, the intermediates topic is getting over. Now let's enter into the next topic, which is called as electronic displacement effects. Okay, electronic displacement effects. So we are going to discuss about the three effects: inductive effect, hyperconjugation, and resonance effect or mesomeric effect. Okay, resonance effect has one more name, which is called as mesomeric effect. So first, let's enter into the inductive effect and discuss something about it. So to start with the inductive effect, I am taking a molecule, okay, with the formula AZ. So this is a general formula for the molecule that I have taken. And you all know that one bond, one covalent bond will have two electrons, right? One bond will have two electrons, and the two electrons are mentioned here. Now what will happen, since both the bonded atoms are different, both the bonded atoms are not same, they are different, right? Since they are different, suppose, let me say that atom Z is highly electronegative in nature. If atom Z is highly electronegative, what will happen to those two electrons? Two electrons, one belongs to A and the other one belongs to Z. But if atom Z is more electronegative, it means that Z is having the ability to pull the shared pair of electrons towards itself. So, the atom Z will pull the electron of atom A also towards itself. Okay. Since it is gaining the electron from A, it takes the partially negative charge, and since A is losing its electron, it is taking the partially positive charge. Okay. So if I put a delta like this is called as delta. Okay. It means partial. Delta means partial. Partially negative, partially positive. It is not completely plus and minus. Okay. It is partially positive and partially negative. Got it? So what is happening? Polarity of the bond is happening. Bond is getting polarized. So this polarity is caused here in the sigma bond. Polarity is caused in the sigma bond. Pi bond means that should be two bonds, right? One will be sigma and the other one will be pi. And we have only sigma bond here in this molecule. The polarity is caused in the sigma bond. Why it is caused? Because of the electronegativity difference between the bonded atoms. Okay. Suppose instead of two atoms, if I have more than two atoms like this, so what will happen? So here you see, I have a molecule like this. I have a molecule like this, and the Z atom is bromine. Or let me take the Z atom as chlorine. or fluid? Let me take this Z atom as fluorine. So now if you compare these two elements, carbon and fluorine, fluorine will be highly electronegative in nature, right? So it will pull the electrons towards itself. So we get partially positive and partially negative. Then if you go beyond this carbon, then also the bond is getting polarized, but partially positive. And still if you go, we are having 3 delta plus, and still if you go, we are having 4 delta plus. Okay. So beyond that, even if you have some carbon attached to it, the bond will not get polarized. The bond will not get polarized. It is a distance dependent effect. It is a distance dependent effect. Okay. It is a permanent effect, and it is a weakest effect. It is significant. It is possible only till third carbon or fourth carbon. That's why I said it is a distance dependent effect. If the distance is more, the effect will be less. So it is inversely proportional. Inductive effect is inversely proportional to the distance. If the distance is more, then the inductive effect will be observed in the very least amount. Okay. Is it clear to all of you? If I have 50-50 percentage separation here, then here I will have only 25 percentage separation. Here only 12.5 percentage. So like this it goes on, and at one point it stops. That point will be the fourth carbon. That point will be the fourth carbon. 1, 2, 3 and 4. Okay. So can you able to understand the inductive effect? So Pragati is asking me one doubt that ma'am, all are all partial charge of carbon atom is due to, yeah, it is all due to the electronegative atom only. It is all due to the pulling of electrons of Z. Okay. So if you don't have any electronegative atom attached to some atom, then you will not observe this inductive effect. Okay. Electronegative atom will be there, or electron withdrawing group will be there. So anything can be attached. Okay. Electron withdrawing group also has electronegative atom inside it. Is it clear, Pragati? So if you have the same atom attached to each other, then you will not observe this inductive effect and all. Okay. So only if some electronegative atom is there, you can observe it. Clear? So the very important point that you have to keep in mind is the bond is getting polarized. The polarity is caused in the sigma bond due to the electronegativity difference. It is a distance dependent effect. Okay. So now let's go into the two types of inductive effect. One is minus I effect and the other one is plus I effect. Positive inductive effect and negative inductive effect. So what is meant by plus I effect? So in case of plus I effect, which is positive inductive effect, the electrons are shifted towards the carbon chain. Electrons are shifted towards the carbon chain. You see here, we have a carbon chain. Electrons are moving towards the carbon. Okay. And which group can cause this plus I effect? Electron donating groups leads to the plus I effect. Okay. Now, who are those electron donating groups? These are the electron donating groups. CH2 minus, carbanion, NH minus, O minus, SiR3. So all these are the electron donating groups. The very important electron donating group is the alkyl group. Okay, alkyl groups. Clear? Methyl, ethyl, propyl, and this one is amine and oxygen containing group. All these are electron donating. If electron donating group is acting as a Z here, then all the electrons will move towards carbon, or I can say the group which is attached here is donating the electron. Okay, so that's why it is called as plus I effect. All right. Now talking about minus I effect, it is the opposite of plus I, right? Minus I, negative inductive effect. So here, all the electrons are shifted away from the carbon chain. It means the atom Z will pull the electrons towards itself. So electron withdrawing group will show this effect, minus I effect. So who are those electron withdrawing groups? So this is a list of electron withdrawing group. Okay. So NH3 plus can withdraw the electrons more effectively compared to NO2. So I will just give you, I will underline the very important electron withdrawing groups that you should know. Carboxylic acid and CN also. They're all halogens. Yeah, that's it. So these are the very important electron withdrawing groups that you should know about. Okay. And the order of inductive effect is determined experimentally. So how we are giving this order for these effects? It is experimentally determined value. Okay. Here also you see we have SH and OH. Sulfur and oxygen both belongs to the same group. And also we know that oxygen is more electronegative. So if something is more electronegative, it will withdraw the electron towards itself more effectively. Right? So what should be the order? OH should have the highest pulling tendency compared to SH. So the order should be like this. We should have OH here and SH here, but it is in the other way around. So SH is pulling the electron more effectively compared to OH. Okay. So that's why I'm saying that it is, this effect is, the order of inductive effect is determined experimentally. Experiment shows that SH attached compounds are having the more effective minus IF. Okay. Electron withdrawing nature of SH is more compared to OH in the experiments. Okay. So you don't have to worry about the order. You don't have to memorize the electron donating and electron withdrawing groups given in this. So just learn the groups which I have underlined. That is enough for you. Okay, there are two types, plus I and minus I. Plus I means electron donating group and minus I means electron withdrawing group. So, okay, electron donating means alkyl, NH2, OH, those will come. And electron withdrawing means electronegative atom contain NO2, C and COH. First case, will first carbon have the highest? Yes, my dear, in all the cases, the one which is having or the one which is near to the group will experience the highest charge, whether it is positive or negative. Okay, because that carbon is adjacent to this group, right? Suppose if I have C, C, C and NH2. So NH2 is an electron donating group. Since this carbon is very near to the electron donating group, so the charge separation will be more between these two atoms. Clear? Or thus, this carbon will experience more electron-rich capacity since it is gaining the electron more effectively from NH2. Is it clear for Pragati? Able to understand? Shall we go for the second effect? Okay, all right. So now let's go for hyperconjugation. Let's go for hyperconjugation. To be very simple, to give the explanation or to give the definition for hyperconjugation in a very simple manner, it means helping. Hyperconjugation means helping. Now let's see who is going to help which element. Okay. So here what happens, the sigma bond orbital overlaps with the p orbital. Sigma bond orbital overlaps with the p orbital. Okay, sigma bond forming or compound will be the hybridized one. So mostly sp3 hybridized orbital will overlap with the p orbital. Okay. So this is what happens here in hyperconjugation. Now, more the number of alpha hydrogen, more the hyperconjugative structure. So more will be the hyperconjugation effect. So if you have more number of alpha hydrogen, your compound is the given compound will have more number of hyperconjugative structure. So what I can write is number of hyperconjugative structures is directly proportional to the number of alpha hydrogens present in it. Okay. Suppose if a compound has 6 alpha hydrogen and the other compound has 9 alpha hydrogen, the compound which has 9 alpha hydrogen will have more number of hyperconjugative structure, right? And the effect will also be more in that case. Now you may ask me, ma'am, which is alpha hydrogen? Which is called as alpha hydrogen? I will tell you what is called as alpha hydrogen. Okay, don't worry. Now hyperconjugation is observed in carbocation. It is observed in carbocation. So the hybridization of carbocation is sp2 and the hybridization of the adjacent carbon is called as sp3. So this is the carbon which is adjacent to carbocation called as alpha carbon. So the number of hydrogens attached to this alpha carbon is called as alpha hydrogen. So who is this hydrogen? This is called as alpha hydrogen. Okay, so we have only one alpha hydrogen. So that hydrogen will go out as H plus, leaving its electrons here. So what will we get? We will get a pi bond. The hydrogen will go out as H plus. So this is how they help each other. Okay. Carbocation means it is electron deficient in nature, right? So to help that carbon, the alpha hydrogen is helping. It is leaving out as H plus and by giving its electron to the carbocation. Okay. This is called as hyperconjugation. Now let's study the stability of carbocation. I have already told you that tertiary carbocation is more stable. Okay. Hyperconjugation, hyperconjugative effect, both are more or less same only, my dear. Okay. Hyperconjugation and hyperconjugative effect, they are same only. So talking about the stability, I told that tertiary carbocation is more stable. Right. Now, in terms of hyperconjugative structure, if I want to define the stability, stability is directly proportional to number of hyperconjugative structure. Okay. So if a compound can give more number of hyperconjugative structure, then that compound will be more stable. Okay. So based on that, we can solve this. We have already discussed this. Just now in the stability of intermediates, I have discussed, right? So what is this? CH3 plus is the methyl carbocation. Methyl carbocation doesn't have any alpha carbon. So there is no alpha hydrogen also. Zero alpha hydrogen. And here I have one alkyl group, which is CH3. So I have RCH2 plus, which is primary carbocation. And here I have 3 alpha hydrogen. So this is the alpha carbon and this carbon has 3 hydrogen. And in the secondary carbocation, we have 2 alkyl groups and there are 2 alpha carbon and there are 6 alpha hydrogen. Okay. And in the tertiary system, the last compound, we have 3 alkyl groups. So there are 9 alpha hydrogen. So if the number of alpha hydrogen is more, number of hyperconjugative structure is more. Stability will also be more. So now you tell me which one will be more stable. Which one will be more stable? The one which is having 0 alpha hydrogen or the one which is having 9 alpha hydrogen? Which one will be more stable? Methyl cation or tertiary cation? Very good. So the one which is more stable is the 9 alpha hydrogen containing compound, right? So the tertiary compound will be more stable. Okay. So I said that I will give the reason in the upcoming effects, right? So this is that reason. The more number of hyperconjugative structure gives the stability to that compound. All right. This is all about the hyperconjugation. Okay. So we have completed inductive effect and now we have completed the hyperconjugation also. So now let me go with the third effect, which is called as resonance effect. But before moving on to the resonance effect, we should know the meaning of resonance, right? Can anyone tell me the meaning of resonance? Have you heard of this term resonance before anywhere? Resonance means similar? No. Give a try, give a try. Okay, no problem. I will give the definition, okay? Just listen. Delocalization of pi electron is called as resonance. Multiple ways to form a bond. Yeah, multiple ways to form a bond. All right, somewhat similar. So the delocalization of pi electron will lead to the multiple ways to represent a compound, which is called as resonance. Okay. The delocalization of pi electron is called as resonance. Got it? Now I will give you one example. I will take benzene as an example. C6H6 is called as benzene. And we have three pi bonds. Three double bonds are there, right? So we have three pi bonds. And the hybridization of all the carbon will be sp2. So there will be one empty p orbital for all the carbon atoms in the benzene. And these are those 6p orbital which is present for benzene. Okay. As you can see that benzene has 6 sigma bond. 1, 2, 3, 4, 5 and 6. Okay. We are not going to study about those sigma bonds. We are going to learn about the pi bond. So how many pi bonds we have? So this is one pi bond. And what is this? Let me erase. Okay. And this is the other representation of the pi bond. So what has happened here? I have delocalized. I have shifted this pi electrons here and this here and this here. So which leads to this structure. Then again, if I shift back these electrons, I will get back the first structure. Okay, and this is the second structure. So what is happening? The pi electrons are getting delocalized over the 6p orbital. Okay, the pi electrons are getting delocalized over the 6p orbital, and this is called as resonance. So using this concept only, we are going to learn the resonance effect, okay, which is otherwise called as mesomeric effect. So as we have studied, the displacement of electron in molecule through resonance is called as resonance effect, and this effect has two types like inductive effect. One is called as plus R effect or plus M effect, and the other one is called as minus R effect or minus M effect. Okay, so there are two types of resonance effect we have. So I will first discuss about the plus R or plus M. Okay. So in case of plus I, what we have studied, plus I groups are electron donating groups. And here also plus R groups or plus R effect means which donates electrons to the carbon chain. The one which donates electrons to the group which donates electrons to the carbon chain is called as plus R groups, and the effect which is experienced is called as plus R effect. Okay. So and the condition is the attached atom has at least one lone pair. The attached atom, the group, should have at least one lone pair or extended conjugation with the pi bond. Extended conjugation with pi bond. I will give you one example. Listen. So here I have a compound, and the name of this compound is phenol. Okay. And this is the group which is attached. And this group has two lone pair of electrons. This group has two lone pair of electrons. So at least one lone pair should be there. This compound has two lone pair. So now what will happen? One of the lone pair will be coming towards the ring, phenyl ring, and one of the pi electron will be shifted to the adjacent carbon, and they lead to this structure. Okay. So again, what will happen? The negative charge will come inside, and the next pi bond electron will be shifted towards the adjacent carbon, and they lead to this structure. And then what happens? It keeps on rotating like this, leading to fourth structure, and the fourth structure, the negative charge will get delocalized like this to give back the first structure, which is similar to the fifth structure, which is similar to the first structure. Okay. So what is this? What is happening? Delocalization of pi electron is happening inside this. Okay. So if this has to happen, the compound should have at least one lone pair of electron or extended conjugation with the pi bond. So this is called as extended conjugation with the pi bond. Conjugation means alternative. Okay. One double bond, one sigma bond, and one double bond and one single bond. So that is called as conjugation. So the extended conjugation means we should have at least more than 2 pi electrons, pi bonds. So that is called as extended conjugation. So this type of system will lead to the delocalization, and that is called as resonance. Okay. So all electron donating groups will show plus R effect. All electron donating groups will show plus R effect. Okay. Now let's go for minus R effect. As you know, minus R effect is the opposite of plus R. If plus R is donating, minus R means withdrawing the electron from the carbon chain. Okay. The attached atom should have pi bond with more electronegative atom. I will give you an example. Listen. Now here, in this group, in the group which is attached to the phenyl ring, the group is NO2, right? It is called as nitrobenzene. So it has NO2 group. NO2 group has 2 electronegative atoms. And those 2 electronegative atoms are oxygen. So what they will do, they will withdraw the electron from the ring. They will withdraw the electron from the ring leading to this structure. Now to help this carbocation, the adjacent pi electron will come and get shifted like this, which gives rise to this third structure. Then the adjacent pi bond will come and help the second carbocation, which will give rise to the fourth structure. Then one of the pi electron will come back here, and the negative charge on oxygen will again get rearranged to give the last structure. So what is happening here? The group which is attached to the ring is withdrawing the electron from the ring. So those groups are called as minus R groups, and the effect observed in such compound is called as minus R effect. Okay. Is it clear to all of you? Shall we go for the list of plus R groups and minus R groups? Shall we go to the list of plus R groups and minus R groups? Okay, I will give you the list. The plus R groups are OH, NH2, NR2, OR, OCOR, NHCOR, CH3. Pragati, they withdraw the electron because of their electronegativity. 2 atoms, 2 oxygen atoms and 1 nitrogen atom, all the 3 are more electronegative, right? You know that electronegativity means the pulling of electrons towards itself. The tendency of an atom to attract the shared pair of electrons towards itself is called as electronegativity, right? So because of its electronegativity only, it is pulling the electron. It is withdrawing the electron from the ring. Okay, from the phenyl ring. Okay, is it clear? No, stability in the sense, here we don't relate the withdrawing effect with the stability and all. If we compare 3 different or 4 different compounds in which we have different groups attached, there we will discuss about the stability. Don't worry, I will discuss those things in the next slide. Okay, I will discuss about the stability later. In the next slide, I will discuss. Yeah. So now here I am giving you the list of plus minus R groups. Just take it down. Very important list it is. Minus R means NO2 containing compound. Just now we have seen NR3, sulfonic acid, CF3. Because of 3-fluorine, it will act as an electron withdrawing. And here also chlorine. Chlorine is also electronegative. So because of chlorine, it will act as electron withdrawing. And here carboxylic acid, aldehyde, and ketone. So all these compounds will act as an electron withdrawing group or minus R group, and the other way around, here all of them are electron donating groups or plus R groups. Okay. And also one more very important thing. This particular mesomeric effect acts only at ortho and para position, not at meta position. Okay. It acts only at ortho and para position, not at meta position. Okay. So in the previous resonance structures also, if you have noticed, the positive charge and the negative charge got delocalized only at ortho and para position, not at meta position. Okay. So just take down this point. Now let me explain you the applications of this mesomeric effect or resonance effect. So starting with the stability of carbanion, you all know that carbanion is an electron-rich species, right? And the stability is in proportional to electron density. It means stability is directly proportional to minus M group, and it is inversely proportional to plus M group. If I have electron withdrawing group attached to the ring, then that compound will be more stable. If I have electron donating group, then the compound will be least stable. I will give you one question so that you can understand. So now you compare the stability of the following anions. I will give you 3 anions. So listen, there are 3 carbanions. Okay. So for all the 3 carbanions, this part up to this part, it is same. So what is the only change? So in the first molecule, I have CH3 group attached. CH3 group is an electron donating group, right? Electron donating group. And here I don't have any groups. I have only hydrogen attached to it, to this ring. And here I have NO2 group. NO2 group is an electron withdrawing group. It will withdraw the electron from the ring. Okay. So electron donating group means it is plus M group. So plus M group is inversely proportional to stability. So if I'm having plus M group or electron donating group, then that will decrease the stability. That is the meaning, right? So that will decrease the stability. So among these 3 compounds, the first compound is least stable. Okay. And coming to this NO2, NO2 is an electron withdrawing. Or I can call this as minus M group. It is also called as minus M group. If I have minus M group, then what will happen? The stability will be more. So minus M group stability is directly proportional to stability. Okay. So minus M group is there. So the given compound will be more stable for carbanion containing species. For carbanion containing species. Clear? Is it clear now? So just take down this relation. If you're having electron withdrawing group attached to the carbanion containing ring, then that will be more stable, and electron donating group containing carbanion will be least stable. So is it clear now? Pragati, has your doubt got solved? Shall we go for the next slide? Now next I will go for the acidity of reagents. Using the mesomeric effect, you can find out the acidity also. How? Acidic strength is directly proportional to Ka value, but in all the questions, Ka value will not be given. Now, how to find out the acidic strength using mesomeric effect? If the electron is taken, how will it become more stable? Carbanion is electron rich, right? One side electron donating group is there, which is the carbanion. And on the other side, we have an electron withdrawing group. And the phenyl ring is also electron rich. Clear? Phenyl ring is also electron rich. So if one side it is giving, one side it is taking. So that system will be more stable. In case of the first compound, if you see, one side electron is donating, the other side also electron is donating. Okay, both the sides electrons are donated to the ring. So that compound will not be that much stable. It will not be that much stable. The resonance cannot occur. Okay. Yeah. So talking about acidity. So if you want to find out the acidic strength using this mesomeric effect, then you should follow the relation which I am giving. Okay. Acidic strength is directly proportional to minus M effect. Acidic strength is directly proportional to minus M effect, and it is inversely proportional to plus M effect. It is inversely proportional to plus M effect. Okay. So now I will give you one question. Just listen. Compare the acidic nature of the following compounds. So here I have got 4 compounds. Okay. So among these 4 compounds, we are going to find out which compound is more acidic. So in all the 4 compounds, this part is same, right? We have COOH attached to all the groups. So this part is same. Now let me start from the first. So for the first compound, I have CH3 group. CH3 is an electron donating group, which is called as plus M group. Okay. And in the second case also, I have CH3, but it is attached at the meta position. Okay. So it is acting as a plus I group, not plus M group, because plus M means it is possible only for ortho and para. It is not applicable for meta. So if something is there at meta position, we have to take that as plus I group, inductive effect. Okay. Then for the third compound, we have NO2 attached. So it is an minus I group, and para position, the last compound has NO2 at the para position, which is taken as minus M effect. Okay. Now, acidic strength is directly proportional to minus M group. So which one is more acidic? The minus M containing compound is more acidic. The last compound is more acidic. Okay. And the first compound is least acidic because it is inversely proportional. Acidic strength is inversely proportional to plus M. Inversely means if one is higher, the other one will be lower. Okay. So if plus M group is effect is there, then acidity will be very less. So that's why this compound is least acidic in nature. Is it clear to all of you? Students, can you able to understand? Can you able to understand? All of you? How do we compare between minus I and, yeah, that I have told, no. Electron withdrawing groups are called as minus I. Electron donating groups are called as plus I. I have given you that list, right? Using that list only. But that list will be same for most of the thing. Okay, electron donating means alcohol, amines, alkyl CH3. So those will come. Electron withdrawing means NO2, COOH. So that list you memorize. So you apply that list to both the inductive as well as for mesomeric. It will be more or less same only. All right. Yeah. So now we have discussed all the 3 electronic displacement effects. And the next topic that we have to move on is the aromaticity and the types of organic reactions. Okay, all the reactions in organic chemistry. So I think we can start that new topic, which is the last topic of this lesson in the next class. All right. So do you guys have any doubt from today's topic from the electronic displacement effects? Do you have any doubt from the electronic displacement effects? And from the 2 intermediates, we have discussed about carbanion and carbocation, right? So if you have any doubt in these 2 topics, you can ask me now. You have any doubts? All right, then we can meet up in the next class. Okay, mostly in the next class, we can complete this lesson. And if time permits, we can solve some questions also from GOC. Okay, clear? There is no much application in inductive. It is not induction, Pragati. It is inductive effect. Application means you can take this as an example. This is also an application only, right? So this one, the order. You can find out the acidic nature from the inductive effect. If you're having minus I effect, it will be more acidic. If you're having plus I effect, it will be least acidic. Got it? So you can find out the acidity, you can find out the stability. So again, acidity, basicity, stability, this will be the applications for all the effects. So you will understand the effects. You will understand the importance of these effects and applications of these effects more effectively in the upcoming organic chemistry lessons. Okay, when I'm discussing about each and every compound, during that time you can understand the acidity of those compounds. Okay, which follows this effects: resonance, inductive, and hyperconjugation. All right, clear? Okay. If there are any more doubts, you can ask me. Otherwise, we can meet up in the next class. Thank you so much for all of you who have listened to today's lecture. Thank you so much, students. Take care. Bye-bye.